Hi, everybody. This is the first in a series of short videos where I'm going to go over examples of the sort of things you should know coming into Calc 2, but also coming out of Calc 2. So first I'm going to do some review examples, and then examples of applications of integration, examples of integration techniques, examples involving sequences in series, and then examples involving power series. So today I'm going to do the first example of something that you should have learned in Calc 1 that I think is important for you to remember as you go into Calc 2, if for no other reason than for the concepts behind it. So let's take a look at that. All right, so in this video we're going to focus on the definition of the derivative. So the question we're trying to answer is, or the task we're trying to complete is to find the slope of the tangent line to a function. So I have this function in blue, and the tangent line is this red line, and the problem is I want the tangent right at the point where x equals 1. But that's only one point. And in algebra and in pre-calculus, when you find lines, you need to find the slope, but to find the slope you need 2 points. So right now we can't find the slope of this line, and so we need to do something different. So what we do to find that slope is we start with an approximation, okay? And we approximate with this line here called a secant line, all right? So this secant line passes through the one point we're interested in and then some other point, but because it's passing through 2 points, we can find its slope. This expression here, f of 1 minus f of 0 over 1 minus 0, that's our change in y over our change in x, and that expression is called the difference quotient. And using that difference quotient, I get that the slope of that secant line is -1. Okay, so that secant line is a very rough approximation, very, very rough in this case, of the tangent line. And so the slope of the secant line is a rough approximation of the slope of the tangent line. If we move the second point closer to the point we're interested in, we get a slightly better approximation. And again, I use that difference quotient to find the slope of the secant line, and I get that the slope of this secant line is -3/2, which is closer to the slope of that tangent line. We can continue to do that, and this is why I wanted to do this going into Calc 2, even though this is a Calculus 1 idea, is because I want to emphasize this idea that we have a value we're interested in that we can't find directly. And so we approximate it, and then we keep refining our approximations over and over again. And then what we do is we take a limit, and that limit of those refined approximations give us our actual value. So here I have f of 1 minus f of x over 1 minus x. There's my difference quotient. But now instead of plugging in a specific value, I just put in x. That gives me this expression, which simplifies to x squared minus 1 over 1 minus x. X squared minus 1 is a difference of 2 squares, so we can factor that into x minus 1 times x plus 1. But x minus 1 over 1 minus x, when I divide x minus 1 by 1 minus x, I get a -1 as long as x doesn't actually equal 1. And then if I take the limit of what I have left as x approaches 1, I get -2, and that will be the slope of my tangent line. So we found the slope of the tangent line. We found the derivative by approximating with secant lines and then refining our approximations a little bit at a time, and then taking a limit of that refining process to get the exact answer. That is an important concept behind calculus, whether it's Calculus 1 or Calculus 2 or Calculus 3 or differential equations. This idea that you start with an approximation and then you refine that approximation using repeated refinements of it, of the approximation, and then you take a limit to get the exact answer. Okay, that is a central concept of calculus and why I think this is important. Okay, all right. In general, here is this limit notation. This example, I found the derivative at a point. Here I'm finding the derivative function. Here's our good limit notation. There's our difference quotient. Here, h represents the distance between the point I'm interested in and a point a little ways away from it. Hopefully you saw this expression in calculus. Again, we do a lot of algebra. We cancel out some common terms. So I have a negative x squared and a plus x squared that cancel. And then I could factor out an h and cancel with the h in the denominator. And then I take the limit as h goes to 0. And what I'm left with is negative 2x squared. And that is the derivative function. That's the derivative sort of in general at any given point. And if I plug 1 into that, I get h prime of 1 is negative 2 times 1, which is negative 2. And again, that's the slope at this specific value. Okay. All right, so that was the definition of the derivative. That's this talk. The next talk will be about Riemann sums, which moves us into discussing integrals.